And in this unit, we're going to discover main properties and ways of determining the polynomial functions, as well as defining in general what are polynomial functions. And I believe you have an experience with factoring and simplifying expressions. So I'll keep this part for you as a self-practice, as a part of your home assignment for the next class. And part of skills and concepts you need to know. Here's a simple exercise on simplifying expressions, factoring expression, solving equations. And this would be a crucial part of unit about polynomial functions, because polynomial functions are usually consists of multiple terms. And in order to work with polynomial function, we have to be able to distinguish them from one another. So I suggest we start our investigation of polynomial function with an assumption. So here is an example where Bess knows that linear function result in graphs of straight lines, while quadratic function result in parabolas. And she wonders what happens when the degree of a function is larger than 2. And she searched up a polynomial function on the internet, and she found certain table of values, or table of expressions. Let's take a look on the left and right hand side. What I like to say about math in general, that we have to look for similarities and we have to compare, what we see. And here, the table on the left, it says that these are polynomial expressions, and the table to the right-hand side that are not polynomial expressions. And first thing first, I would like to notice is that we have a certain power of expression. And in polynomial functions, the power of an expression determines by the greatest power of a variable in this expression. For example, the first example in the left table, you can see that the power of this expression is 2. So this is a quadratic polynomial function. Meanwhile, the expression that is number 4 in this list has the greatest power of 3, which means this expression is of the third power. Secondly, talking about polynomial function, we have to distinguish that polynomial function is possible when it shows the regular function dependence, where we have one dependent variable and one independent variable. So to the one hand, for example, to the right-hand side of the equality sign in a polynomial expression, you're supposed to have only one variable. For example, if you take a look on the table to the right-hand side, you can see in the second from the bottom example, we have x and y variables combined together, which means this expression cannot be called a polynomial. So these are differences and similarities that we can see right away. And one more, let's compare first one on both of the tables. And first thing first, I can notice that power of an unknown variable on the left-hand side, where it says that these are polynomial expressions, powers of an unknown of the independent variable are listed in order of decreasing. So we have power number 2, first power, and 0 power here. If you look at this constant 3, so we add up 3, it means that basically we can express it as 3 times x to the power 0. So we say that the power of a independent variable of 3 equals 0, x to the power 0, because any number to the power 0 equals 1. So once again, powers are listed in an order for decreasing, while on the right-hand side, we can see that the power for x is 1 over 2, and this means that it's less than power 3 that we have to the right from it. And it states that in this case, they're not listed in the proper order, so we cannot call that a polynomial expression as well. So talking about polynomial expressions, and they are one variable. So a polynomial expression in one variable is usually written with the power range from the highest to lowest degrees, as in an example for example, 3 to the power x squared subtract 5x plus 3. The phrase polynomial expression is also shortened to just polynomial function. Do you have any questions about this, about how we distinguish polynomial expressions and polynomial functions? Yes, sir? No, perfect. So suggest we move on. So considering the polynomial functions, the simplest polynomial functions are functions that contain a single term. So as we said in the previous part, we had base functions like x squared or square root of x. Talking about polynomial functions, the simplest polynomial function would contain only the independent variable to a certain power. So it could be power 1, 0, 2, 3, 4, etc. And if you look here, you can see that we have generally, we never go higher than a quintic exponential polynomial function, which is a greatest power of 5. But in general case, in mathematics, you will face various polynomial function. And let's write down the equation in general form for polynomial functions. So polynomial function f of x going to have a form of an, where an is a certain constant multiple, an times 2xn plus an minus 1 times x to the power n minus 1 plus a to the n minus 2 times x to the n minus 2, and plus and so on up to infinity. We can list as many as we want, but it will end up with a 2x squared plus a 1x to the power 1 plus a 0 times x to the power 0, but we can simplify it and write it as 1. So this is a general form for polynomial functions. And whenever you work, oh, sorry. Well, let me get back to the page. Yep, here. So whenever you work with polynomial function, any polynomial function you're going to see going to look like this. And here you can see that we start, whereas n is the greatest power of this polynomial expression. For example, if the greatest power was 5, and we will substitute n for 5, n equals 5. We substitute into equation, you can see that a5 is some constant multiple. We don't know this value right away. But for example, if we have expression 5 to the times x to the power 5, in this case, an would be equal to 5 plus, for example, 3x to the power 4, an minus 1 would be 3, and so on. Is there any question about the general form of polynomial function? important thing to note is that all of these constant multiples are going to be real numbers. If you don't have any questions, we'll move on from here. You can find this this expression here in the Nielsen textbook on page 125. I'm also going to have it at the end of this paragraph. So please remember that the polynomial functions are named according to their greatest power, like linear, quadratic, cubic, quartic, and quintic functions. Okay, great, Yasser. Thanks for submitting your test. I'll check it and issue the mark. So these are general and most important understanding of a polynomial functions. And let's summarize the key ideas, because this is just an introduction to polynomial function. We have to understand and identify the general form of a polynomial function, which is expressed as one variable in an expression, and we have relation as f of x equals an xn plus an minus 1 x to the power n minus 1 plus and so on up to a0, and where n and a are real numbers, real whole numbers. Remember, the power of a independent variable cannot be a fraction. See here in the table that show us not polynomial expressions, you can see that the last one, we have 3 times x cubic plus 4 times x to the power 2.5. And that's not the case for us. We cannot have a fracture power. We don't work with them. Even though theoretically you can find it, but we can't. We cannot do it algebraically. So, and you need to know for sure that in any polynomial expression, the exponents on the variable must be whole numbers. That's what I was saying just a minute ago. Polynomial function is any function that contains a polynomial expression in one variable. So, as an example is 5 times x to the power 4 plus 3 times x to the power 3. These are one variable with exponent, and the degree of the function is the highest exponent in it. For example, this example where 6 times x to the third power subtract 3 times x squared, the degree of this polynomial function is 3. The infinite differences of a polynomial function of degree n are constant. The domain of a polynomial function is the set of real numbers. The range of a polynomial function may be all real numbers, or it may have a lower bound or an upper bound, not both. The graphs of polynomial functions do not have horizontal or vertical asymptotes. So to remind you, if we have a graph, horizontal and vertical asymptotes, I'll use different color, let's say blue. Vertical and horizontal asymptotes are lines that the function is trying to approach, but would never cross them. And polynomial functions do not have those asymptotes. They only have bounds, lower or upper bounds. For example, like quadratic function of hyperbola oh, sorry, of parabola. It has the lower bound here where function changes its direction. The graphs of polynomial functions do not have horizontal or vertical asymptotes. The graphs of polynomial functions of degree 0 are horizontal lines. That's obvious because if x to the power 0 equals 1, it means the graph of this function would look like, for any value of x, the value of y would be unique. Not unique, it will be single, it would be 1. It will be just a single horizontal line. The shape of the other graphs depends on the degree of the function. 5 typical shapes are shown for various degrees. And let's take a look at it. It's really important to know shapes of these graphs because later on we'll work with graphs and we'll have to find a corresponding polynomial function to it. And if you know that these 5 general shapes of a polynomial function, it means that you can easily distinguish them from one another because these shapes like parabola, then this curve for cubic function, they all are repeating themselves. For example, you can have this function 6 times x to the third power, or you can have 5 times x to the third power, or you can have negative 105 times x to the third power. It doesn't really matter. The shape of this graph will remain the same for all of these cases. Please review this at home. Use your graphical calculators just to get familiar with it. Just type in random polynomial function and see what output you get. Try to play with the constants. Try to change the constant multiples because you'll see how it affects the shape of the curve. So yes, sir, do you have any questions about this so far? Okay. I hope you understand everything. In case if you have any questions later, please don't hesitate to contact me. And now, I suggest we do a little practice and exercise together. Which one? Let's do example number 4. And it's going to give us good understanding of this unit. So graph the function y equals 2 to the power x on the domain from 0 to 3. Explain why a person who sees only the graph you created might think that the graph represents a polynomial function. Explain why this function is not a polynomial function. Okay, no problem with that. Let's start with creating a coordinate axis, y-axis, x-axis, x and y here, and domain from 0 to 3. So 0 and 3. This is our domain. To mark my domain, I'll use 2 dotted lines. One vertical lines like this. And I have function 2 to the power x. So yes, sir. How would you start sketching this graph? Would you create a table of values, or would you find zeros of this function? Let's make a table of values. So x and y values. Let's take at least 3. Let's take in the range from 0 to 3. So I would take 0, 1, and 3. We'll see, take notice that 0 and 3 are included in our domain. So when x equals 0, function y equals 2 to the power x would take value of 1, because 2 to the power 0 equals 1. And when x equals 1, y would be 2. And if x equals 3, y would be equal to y would be equal to 8. Am I right? 2 to the power 3, it's 2 times 2 is 4, times 2 is 8. Great. So let's plot these points on the graph. x0, y1, x1, y2, and x3, y8. 2, 4, let's say it would be somewhere here. And now look, we have our 3 points, and let's join them with a nice smooth curve. So starting from point 0, 1, right? This is the point 0, 1. Here we're going to have the point 1, 2, 1 for x value and 2 for y values. And remember, this is an ordered pair. This is supposed to be denoted in this exact order, x and y. X and y. So, and third point is 3 and 8. If we join all of these 3 points together, look, we have a nice curved shape. And if some person that sees only the graph we created and not the function we used to create this graph, may really think that this is some kind of a polynomial function. I'll use a purple color to continue the assumption of a regular person. Regular person can say, oh, this is a polynomial function for parabola, it's quadratic polynomial function. And they won't be wrong because they couldn't see the initial function we used to create this graph. They simply couldn't know it. But we know that if we were given with a domain, for example, from -infinity up to 3, we would see that when x takes negative values, our function, instead of growing up, or as it, or decreasing as for quadratic function, we'll get a curve that has a horizontal asymptote, right? Because function 2 to the power x would never be equal to 0, no matter how low x value you take. This function will always try to reach this horizontal asymptote, but it will never cross it. Am I right, yes, sir? So yeah, and now you can see that some random person can assume this is a quadratic function, but we know that it's not. And first of all, because this function has a horizontal asymptote. So this is the answer to question B. Explain why this function is not a polynomial function. And answer A, and explain why a person who sees only the graph you created might think that the graph represents a polynomial function. They might think so because we can see an exponential dependence where the greater x becomes, the faster this curve grows. The same attitude we can see for x squared function, which is a polynomial function, because if you take x 10, we will get y equals 100. But if you take x 12, y would equal to 144, drastic increase, so exponential growth. Can you explain your question, Yasser?
You see how it goes horizontal, the yellow line. When it goes down to zero, zero is included in the equation, right?
0, you mean included in the range or domain?
Yeah, the range.
No. So for function 2 to the power x, 0, the range of this function would be from 0 to positive infinity, where 0 is not included. Because if you take a look here, try to find value of x that will give you y equals 0. There is no such value.
But wouldn't it? But it's technically for the range. We're just talking about vertically, right?
Yes, absolutely right.
So why is it not included if we're just talking about vertically?
So
Because it goes down to zero.
vertically, if you zoom in somewhere here, you see this yellow circle I'm making? If you zoom in somewhere here where x takes super negative values, right? Like negative million, for an instance, you're gonna see that the curve of this graph, y equals 2 to the power x, is not crossing this horizontal line. It's only approaching it at extremely close distance, but never actually crossing it. That's why it's called asymptote.
Because I just realized that made me realize I mixed something up on the test in I think was it I'm looking now, question 4. It was similar like this. I said the opposite. I put the one that has it included, I put it not included, and then the one that's included, I put it and the one that's not included, I put included for the zero.
So it's minor mistake. So I suggest you review your answer for that particular question because you understand what you could have done wrong. I didn't see your test yet. You have chance to resubmit it by the end of this class. So don't worry about it. But I hope you understand my reasoning about that. We have horizontal asymptote in this case, right? Horizontal asymptote restricts the range, and vertical asymptote restricts the domain.
Oh,
Makes sense? Because
see, yes,
vertically,
yes.
if we take a vertical line, it's basically cutting our coordinate axis in x. We're taking certain domain in x when we have vertical asymptote. But when we have horizontal asymptote, we're slicing our range in certain area.
I see. Yeah, because it messes it up. Yeah, you're right.
So don't worry, you're a smart student. I understand that you could have made an unfortunate mistake as you've been worried or in
That was
rush
it
or
was question
something.
4.
So just adjust your file by the end of this class and submit it.
Okay.
If it's a minor mistake like brackets you used squared instead of round one. I can understand that because I know that
Yeah, it's that.
you in fact you know the difference.
Because it's just the whole question was based off that, explaining it, right? Yeah, that's the only reason why it matters a lot.
So just use the
Yeah.
same paper, cross your answer, cross it out, show that you change it. Don't make it from the scratch. Use the same paper you used. Just cross it out,
It's just a
write a
little
new answer.
bracket. I just changed the brackets.
Yeah, good, good. So do you have any questions about this particular example?
No, I the only thing that was confused me about was the asymptote, because I realized I did it wrong.
But now you know.
Hmm.
So did you copy this down into your copybooks?
Give me a second.
Yeah, sure, take your time. Oh, you copied it down? Okay. So, and I suggest we start a little bit about the characteristics of polynomial functions. And it's pretty interesting part about polynomial functions in general, because after covering this unit, you'll be able to define main properties of polynomial functions, such as how it behaves on infinity, or whether it's odd or even function, based on what you see in the expression. You won't even need to plot the graph in order to define these properties of polynomial function. So let's take a look at these examples of polynomial functions we see down below. Investigation said that Carl knows that he can describe the graph of a linear function from its equation. Using the slope and the y-intercept, we all learned that in the previous courses. And he can also describe the graph of a quadratic function from its equation using the vertex, the y-intercept, and the direction of opening, whether it opens up or down. But now he's wondering whether he can describe the graphs of polynomial functions of higher degrees using characteristics that he can predict from their equations. Let's take a look at a few graphs that we can see here. For example, graph number A, we can see that this is a parabola. This is in fact a quadratic function. So first characteristic, we know that it's going to be this is going to have a shape as follows. It's going to be a parabola. And looking into equation, we can see, for example, the vertical displacement, and so we know that the vertex of this parabola will be displaced downwards for 5 points. And there are many more properties that we can see by looking only at the equation of the polynomial function. For example, greatest power has a great impact on the shape of a curve, because if the greatest power of expression is odd number, then it means we have an odd function. This is what gives us this shape where both lines are ending up at the top. Odd function means that f of x equals f of minus x. So whether you take positive or negative value of an x, we're going to have the same value for same y value in that case. So moving on. So here it's important to notice that this particular parabola is not a even function, because we have 4 times x, which is a odd power. And if you take negative x value, this term would be different from when you take positive x value. But for example, if you have a polynomial function as x to the 4th power plus x to the 2nd power, this is an example of an odd function. Oh, sorry, not an odd, but even function. Moving on to the description, here's what they see. Sorry, this is what they show us. Basically, looking at the expression, we can say what degree this function has. We can say whether it's even or odd degree of this function. We can define the leading coefficient, and the leading coefficient is the constant multiple that is positioned in front of the greatest power of a independent variable. So in this case, if x squared is the greatest power of the equation, the leading coefficient is the multiple that stays in front of it. And in this case, it's +1. And behaviors. And behaviors is definition of a function on how it behaves on infinity. And this is directly related to whether this function is odd or even degree. So I made a little mistake a moment before when I said that only x to the fourth power plus x squared has a odd or even degree. But even this type of quadratic function, where we have 4 times x, also has an even degree, because when we approach x to negative infinity or positive infinity, this notation where x, arrow, negative infinity, it means x travels to negative infinity. Doesn't take value of infinity, but somewhere close. If we take x, some very big negative number, you're gonna get some really big positive number of y. And the same way, if we take x very close to positive infinity, we would get y very close to positive infinity as well. And if you have following end behavior whether you approach x to negative infinity or positive infinity, it does not affect the end behavior. It will be positive. This is an example of an odd degree. No, sorry, this example of an even degree of a function. A number of turning points is basically number of vertex of your function. And the polynomial function of second power has only one vertex. And if we move up, take a look at the example, you can see that the greater the power of the function, the more vertex we can see. For example, here we have a polynomial function of a fourth power, and we can see that we have 3 vertex here. Please note down one more important thing. The leading coefficient of example B is -1. This is the multiple in front of a independent variable of a greatest power. And what it gives us, if we have negative constant multiple, like -1 or -2, doesn't matter, the polynomial function would face downwards, so open downwards. Meanwhile, on the other hand, if we have positive leading coefficient, like in example number A, we can see that the function will open up. It will go upwards. This is one of the characteristics that we can predict based on the information we observe in the polynomial equation. Even function, odd functions, neither even nor odd function. Here it is. You see? Even function, they have symmetry in y-axis. So I was right. We have to have all the x's in the even power. Odd functions, we have to have all the x's or in odd power, which will give us the rotational symmetry. Take a look here. In the even function, we have a actual axial symmetry over y-axis. So basically, you can imagine it as if the mirror was placed on the y-axis, and the curve to the left and right hand side will repeat itself, like mirrored image. While odd functions have a rotational symmetry around the origin. If you make y and x mirrors here, the rotational symmetry would basically mean that you flip the graph over the y-axis and over the x-axis, or over the x-axis first and then over the y-axis. So this is how every odd function will look like. And neither even nor odd function, as in example A, where we have a parabola or quadratic function, we have x to the power 2, which is even power, and x to the power 1, which is an odd power. If they're mixed up together, this is neither even nor odd functions. Yeah, sir, do you have questions about this? Perfect. And also, it is important to understand that knowing how even or odd functions behave, we can define their absolute value. For example, we know that some even function, quadratic even function, would have minimum, absolute minimum value, the lowest point of this curve where it changes direction. This is the lowest value in the range of a function. Meanwhile, absolute maximum would have to be the greatest value of in a range. For this example, where we have neither even nor odd function, this upside down parabola, take a notice, it's upside down because we have leading coefficient -1 in front of x to the power 2. That's why it opens downwards. In this case, the absolute maximum we're gonna have it on the top of this parabola in this vertex. Considering what we already covered about characteristics of polynomial function, I believe it's enough for you to start reading this chapter on your own, reviewing this material, asking any question if you have. I'll submit a home assignment for you to the Google Classroom for these, for unit 3.2 and 3.1.